So for spring, actually, there's multiple ways of making springs. There's one way is to have you can try to have a wire, metal wire, and then you can coil the metal wire into the helical shape to form a spring. So they have a kind of mechanism, looks like this. So they hook up some geometry to both ends of the metal wire, and they start to coil the geometry. So at the end, you have this spiral shape to form a spring. So let's say the diameter of the wire is small d, and if you have n coils, and to form this geometry, you need to have a pulling force P right here and a pulling force P right here. So both P. And right here, you have a capital R. That's the radius of the spring. Okay, so that's everything you need to know for the geometry, to describe the geometry. So, in fact, when you have this pulling force F, it's gonna generate some moment. If you pull here, multiplying if you see from the side, it's actually forming this counterclockwise force. Okay? So there is a moment, PR. So the way they coil the spring is by this moment. Okay, so originally it was a wire, and they have this mechanism. Okay? So they will apply force P with a radius R to form this PR moment. And then, because there's no balance of force, so the metal wire will deform, start to twist. At the end, when they reach N coils and the geometry reaches this form, the force on the both sides start to balance. So that would be the end of the coiling of the spring. Okay, so once you have this, you can take a look at the cross section, make a small cut. Make a small cut right here. Okay, make a small cut. So if you take a look at the small cut, actually there will be twisting torque due to the force generated by the external force. Okay, so there's torsion. This is torsion, right? And also, overall, you have pulling force on both sides. So for every position inside the spring, there's also shearing force. So for the spring, actually, everywhere they are both torsion and shear. Okay? Once the shape is formed, if you one day apply forces, either you compress it or you extend it, that generates both torsion and shear to everywhere, evenly. Okay, so how do you compute the shearing force caused by torsion? So I can call this tau 1. Basically, the equation that we have learned, 16 T over pi d cubed, right? This is what we have learned. And what's the amount of the torque? Basically, PR. So 16 PR over pi d cubed. Okay. How about the shear? For the shear, basically, for everywhere, it's gonna be the forces and then over the effective area. So it's gonna be P over A, the area, if you call this area A, right? However, the spring is in a spiral shape, and also the geometry is very nonlinear. So it's not like a pure regular circular geometry, and then you truly shear it. So by experiment, researchers have found the shearing force is slightly larger than P over A. So the second part, shear 2, is gonna be 1.23 times P over A. So this is like a correction due to this nonlinear geometry. So the shearing force is gonna be slightly larger than traditional cylindrical geometry. Okay, so over here, you can convert this into a different form. And what do we do? So A is pi half of d square, so it's gonna be pi d square over 4, right? So they want to define a coefficient called C. This is called the spring index. They define this, so later on, some derivation will be simpler. The mathematical form looks simpler. So this is a 2r over d. So what is this C? 2r basically is the diameter of the entire spring. Small d is the diameter of the wire. So it's like the ratio of the spring diameter and the wire diameter. It's called the spring index. It's not the spring coefficient. Spring coefficient is K. So F equals to K delta X. But for geometry-wise, there is a spring index just to describe the ratio between the spring diameter 2r and the wire diameter small d. Using that, they will try to rewrite this equation into a certain form. Let's see how I can get that. They want to have 16pr over pi d cubed times something. So how do you equal both? Right here, maybe I don't do it too fast. I try to have 16 here. So later on, I have a 1 over 16 over there, and 1.23 right there. And I keep the p here. I have pi d squared over 4. That's what I had earlier. Okay, that's after plugging in A, right? And I will gradually to get a form like this. So if I want to do that, I will have 16p of p. But I don't want the small, I want to keep the small d. So I will have pi d, but this time q. So I have small d on the top, 16 here. The 4 can cancel out with this one, so I have 4 here. Okay, and then I have an r here, so I have an r here. Okay. And also 2r over d equals to c. So this guy can become 16pr over pi dq times 2r over d. So I can have a 2c and then 1.23, right? So 1.23 over 2, that's gonna be 0.615 over c times 16pr over pi dq. Okay. So overall, the total shear actually equals to 1 plus 0.615 over c times 16 pr over pi dq. Okay, what does that mean? That means traditionally, if you have a cylindrical geometry and if you generate twist, you will have 16 pr over pi dq. But this time you are forming the spring in this particular helical shape. So you generate additional shear, and the shear is 0.615 over c times the of the shear that was caused by pure torsion. So they want to rewrite the equation into this form, so it's easier for you to make this equation more compact. So this parameter was defined as Ks, and it has a name. It's called the shear stress correction factor. Okay. So they corrected due to this fact where you have additional shear. Okay? And this is for static loading. However, when they did some experiments, they realized when it's under dynamic loading, the stress will be different. So they found out the shear for dynamic loading will become 4c minus 1 over 4c minus 4 plus the same thing right here times 16pr over pi dq. So this new factor here is called the Weyl factor. So this researcher must have done some research experiments and realized the shear stress under dynamic loading is not exactly 1 right here. And it varies in different shapes of the geometry. So he must have done some study on different wire diameters and also different spring diameters. and he realized, okay, he can use this equation to model the correction for torsion shear stress while you are applying dynamic loads. Okay, so whenever you see something like this and with a name, that researcher must have done some experiments and then find a closed model. Okay? Now, after those, we are going to talk about how can we study the spring coefficient. The spring coefficient is a little complicated. Let me spend some time and then try to explain how to derive it. So what in the past, when you, for example, buy a spring or you find a description of the spring in a problem or exercise or homework, they always tell you, okay, this spring has a spring coefficient K equals to something. It doesn't tell you how this spring coefficient is being determined. In this course, we can actually start from some physics and then estimate the spring coefficient based on the geometry and also some solid mechanics. So this is what I'm going to do. Before I do that, can you take a picture? So for spring design, you need to know when you compress or pull, you are going to generate shear stress everywhere inside the spring. Okay, it's shear stress, not normal stress. So you are actually shearing the material. And the shear stress you are generating are having two different kinds, two different models. So if you are truly designing a spring, you want to figure out whether your spring is gonna stay elastic, you can use the maximum shear stress model. Make sure it's not over the design limit. Okay. So let me talk about how you can estimate the spring coefficient. So inside the spring, you might need some imagination on this part. So let's make a cut of a portion of the coin. So it's actually like a C shape. You take a C shape out of the spring. So this is one of the C shape, okay? And this is a cross section, okay? Now, if I try to draw this in a more three-dimensional way, it looks like this. Okay, and then now we are going to have a small slice, very thin slice. So this small thin slice is going to be twisted when you apply force. So this is being twisted. You can say it's being twisted, for example, here and here. Okay, being twisted. As you deform the spring, everywhere inside the spring is being twisted a little bit. So for this twisted geometry, if you create an imaginary line to the center. So this is like the center line of the spring. Okay, if every small slice of the spring has one imaginary wire connecting from the disk, this is a small disk, to the center axis. Then from very top to bottom, there are infinite number of small wires that is connecting from somewhere at the center axis to the small disk, right? So as this small disk is being twisted, it contributes a little deformation. So what does it mean? If I exaggerate, if I turn lie down this small disk and draw a line right here. After twisting, what happened? We have if you remember, there's always a drawing like this. There's an angle after twisting, right? So this angle is d, let me use phi, right? This is twisting. So if when I attach a small imaginary wire to one edge of the disk, this disk rotate a little bit. This wire rotate a little bit. So the angle right here is d phi. And for twisting, this phi basically is the deformation of cylindrical geometry. So overall, if I have 1,000 small disks, every disk is responsible for a tiny deformation of the phi, then overall there are like 1,000 times of those tiny deformations. So if I want to see how much deformation is gonna make, I just need to sum up all the d phi. Okay, so this part basically is like a small contribution to the spring deformation. So how do you compute this? You can from the this is from earlier. There's an equation. It's called TL over JG. Okay, this is what for a cylindrical part. If you compute the deformation, how do you compute deformation? It's TLJG. So it was like when we talk about twisting. So over here, the small portion d delta is gonna equals to how many torque is being generated? PR. JG are the geometrical material information, and geometrical information, it doesn't vary. How about L? L changes a little bit, so DL. Okay, so it's contributing a small portion. Okay, so this is DL. Okay, now if we sum up all of these small contribution of the deformation from one disk, if I sum everything up, I have the overall deformation for the entire spring. That's why the delta can be computed by the integral of the whole thing. Okay, and the whole thing is gonna be J can be replaced by certain equation, I forget what I need 64 something. So this is the result. P R Q N D 4 and G. Why is that? Let me see. The total length. Total length. Did I talk about the total length? Total length. Total length should be n coil times the parameters of the, so basically PR, right? A P, two PR, 2 times PR, right? So this portion, the integral of dl equals to the total L. So at the end, 2 times P, no, you don't need P, 2 pi R, 2 pi R. So 2 pi times R times N. So that's why your R, there's one more R here, and one more N. So what happened to the pi? Cancel out with the pi came from the J. So we can check again about, I forget the equation for the area moment of inertia for a circle. For a circle, that would be, so J is 1/2 of pi, should be pi small d, yeah, to the power of small radius to the 4th. So it will be 2, so 32, 2 to the 4th, so 32 pi d to the 4th. That's why over here, J is pi d 4th, 32 to the top, right? And then G remains there. P remains there, R over there. Right here, the integral of L, so 2 pi N, right? So that's why overall, you have a 64 P R to the, really? To the, how come it's Q? PR. PR is right here. Top is PR. Oh, here, here is already Q. Why is RQ? That means R times DL. P, why is it Q here? I forget. So if this one is right, if this is cube, then there's a, if this is square, then this is cube. Okay, then here is square. So I need to remind myself why there is a square. Let me go back to the notes long time ago for TL over JG. Yeah, TL over JG. Yeah, this is actually sorry. This is theta. Theta equals to TL over JG. So theta in our case is phi. So it's phi. Okay, and we are talking about the arc length. That will be delta. So in a small cut, this becomes d phi and dl. Okay, but we are talking about the arc length. So the arc length equals to the angle times the radius. The radius is capital R. Okay. So this is the angular deformation due to twisting, and from the equation from the twisting, your deformation equals to torque times length over J and G, but that's only the angle. If you want to compute the linear deformation, you compute this arc length. The arc length equals to the angle times the radius, R. Okay, that's why, so this equation goes to here, this goes to here. So DL actually equals to PR squared DL over JG. And that's why the overall deformation can be computed in this way. After we have this, what do we do next? After that, we come up with an equation, basically delta equals to 64 PR cubed n over d to the 4th and g. So this is the first time you have learned how the spring deformation is gonna related to not only the force, but also some geometrical and material information. So the total deformation of a spring, that is related to how much force you apply, the spring radius, the big R, number of coils, how many coils you have, small d, the wire diameter, and also G, this is shear modulus. So it's also related to your material. Okay, and how do you compute the spring coefficient K? K right now basically is gonna be the force over your deformation delta, right? So all you need to do is to compute this. So P over delta, then you will have 64, P disappear, R cubed N D 4G, right? So this is the first time you first learn how the spring coefficient can be computed. Spring coefficient is not related to how much force you apply. Spring coefficient depends on the wire diameter, shear modulus, the number of coils, the radius of your spring. So your spring coefficient is a parameter that is only related to material property and some geometrical information. Okay? So that's your spring coefficient. Okay. So this is the introduction for spring design. Now you know how much stress is gonna be formed when you compress a spring or pull a spring. So it depends on whether you are applying dynamic loads or static loads. different amount of stresses. Okay, and if you want to make sure your spring stays alive for a long time, then you can use the material like the model for static loads or model for dynamic loads to make sure what's the safety factor for your spring. Okay, and then if you want to estimate how much spring coefficient you have, now you know how to do it. Okay, it depends on the geometrical information, material property. You now know the spring coefficient. You can even compute the total deformation for certain amount of forces, the delta or the small k. Okay, so that's what I want to introduce today, and you can design your own spring. Any questions? I'm sorry, the internet doesn't work today, so I decided to use the board.